Good morning, students. Today we'll start rigid Rapier. That is what Dornier weaving machines features we'll study. So first feature we'll be studying, that is we'll be looking to the construction of the machine. So see here the construction of the machine. So rigid Rapier is one of the rigid machine, or Dornier Rapier is one of the rigid machine suitable for fabrics from lightweight fabric, medium and heavyweight fabric. That is what versatile, and it is having side frames, sturdy frames, and ensures low level of vibration with the changing fabric width. So you can see this is what here telescopes are there, from where the Rapier rigid rod will be going in and out, here also in and out, and these are called as creel. Accumulator is there, cone, accumulator. In front of accumulator we are having bricks. These are web selectors here. Like this the machine is there. Here the control panel is there, where we can have the input materials, and this is what control box is there, where the cards are stored, electronic cards are stored. So one by one feature we'll be studying. So see here, this is what sequence of Rapier movements. How the Rapier drive is gone, that we will see here. So here half cut shaft is there, that is what drive from the main shaft. So three shafts are there. This is what sleigh shaft, this is what auxiliary shaft, and this is what main shaft. So from main shaft the drive has gone to bigger gear here. From the bigger gear the drive has gone to the backside. Two conjugate cams are there, match cams, and this is what saddle here. So two cams means what? One cam for moving forward and one cam for moving this saddle backward. So this saddle fulcrum is connected to this half quadrant gear here. You can see here. So this is moving up and down. When this is moving up and down, your gear here moving clockwise and anti-clockwise, and bevel is moving clockwise, anti-clockwise. Bevel transfers the drive in vertical fashion from here to here. So this is moving clockwise and anti-clockwise, and your Rapier is going forward clockwise and anti-clockwise. So whenever we are insert, so here Rapier gear is meshing with this, Rapier is meshing its tooth meshing with this gear pinions here, and entry time we can change by this stroke nut is there. So we can move away from fulcrum or towards the fulcrum, so that inward timing of the Rapier inside the shade can be changed. So this is the point the change places is there. So here we can see 250-degree dual is there to insert the peak. So longer dual is there here. So this is what a drive, that is what called a sequence of Rapier movement. So now operation of opening levers. So here we can see at the center two opening levers are there, for one for left hand Rapier head and other for right hand Rapier head. As the opening levers are there to open and close the Rapiers, this Rapier is called as positive Rapier, because there are external means to open the Rapier gripper or Rapier head. So see here what is happening. First, the right hand Rapier, that is giver, comes at the center of machine earlier, and this opening lever first opens it. Opening lever opens it. For the opening lever, the drive is coming from the cam. These are the cam. Two cams are there. One for the left hand Rapier and one cam for the right hand Rapier, and this the drive is coming from the main shaft here. So from main shaft the gear drive is given. Here the backside gear is rotating and this shaft is rotating, and here the cams are there. By moving this cam, we can change the timing of the opening. So here first right hand rapier is opened here. So right hand rapier in open condition, it goes at the center of the machine. Meanwhile the left hand rapier grips the weft and comes to the center here, and it goes inside the right hand rapier. So right hand rapier is open now. So when the rapiers are going backside, this left hand rapier is open and this is closed. The opening and closing is done by the lifting this opening lever up or down. When it goes down, the rapier is open, and when it goes up, the rapier is closed. So we have seen here right hand rapier, it is first open and enter in the left hand rapier, and weft is still in the left hand side control. When both the rapiers are going backside, the left hand is open and right hand is closed here, and this right hand takes the weft to the receiving side. So external openers are there to open and close the what rapier heads. That's why this is called as positive rapier. So see the figure. Now we will see reed motion. So how the reed bit up is going place, that we will see. So here the main shaft is there. Main shaft, the drive on to the gear backside, and here bigger gear is there inside the frame, and this giving drive to this shaft, opening lever shaft. This is what opening lever. On this shaft, each side of frame, left hand side and right hand side, two complementary cams are there. Pair of complementary cam here. Here two cams are there, this one and this one. And here the saddle is there, giving drive to this sleigh shaft. Two cams, one bowl touching to this one cam, another bowl touching to the other cam. These two cams are facing opposite side. One cam for forward movement and one cam for backward movement. So this, what will happen, this sleigh shaft will rocks one time clockwise forward and one time it will go anti-clockwise. So when it moves clockwise, the sleigh shaft goes backside, and when this shaft rocks forward, the sleigh shaft comes forward for the beater. From here the drive has gone, main shaft, bigger gear. From this the shaft is there, and two complementary cams facing opposite side. The drive has gone to this saddle, or it is called as bowls here. One bowl touching to the one cam like plain tapered shading. So this shaft rocks one time forward and one time backward. So this is what reed motion drive. So whenever the sleigh is coming forward, these two opening levers hides in the groove here, in the groove, and the bit up takes without any disturbance. So these opening levers are sitting in the groove when the bitting is taking place. So this is what the reed bit up. So see the drive, how the bit up is taking place. So here we will see the electronics of the machines here, and that is called as what? CAN bus system here. CAN bus. Without CAN bus, the machine cannot be run. CAN bus is the what? Brain of the loom. CAN bus is called as controlled area network. Controlled area network. This is what? Microprocessor. So here we can see here, we can enter whatever the inputs to the machine in the control panel. From the control panel, the signal goes to the card. From the microprocessor cards, the signal goes to the machine, and again it comes reverse from machine. The data comes to the card, and again it is seen on the control panel. So this is what? Bi-directional transfer of your data. So in the control panel, if you give 300 rpm, the 300 rpm goes to this wire, and it goes to the respective cards, and from the card, these are microprocessor card, your 300 digit is converted into binary language, that is 01 language microprocessor code, and this code is given to the machine, and machine acts according to that, because the machine understand microprocessor language, not 300 digital language. So like this, the cards are there in the control box. So here we can see here, so here control panel is there, we can enter 300 rpm, and below the control panel we are having the control box. In the control box, these cards are sitting. So here we can see in the figures, we are having 1 2 3 4 5 6 7 8 9 10 11. So 11 cards are there in this, means 11 electronic functions are there in the machines. Suppose 5 cards are there, 5 functions will be there. If 6 cards are there, 6. 11 cards means very modern machine it is, and advanced technology machines are there. More number of cards, more advanced machine it is. Means all the functions are automatic. So we can see here let off card is there, take up card is there, then accumulator card is there. If accumulator card get damaged, the accumulator function will not start. If let off card get damaged, let off function cannot be started. So this is what CAN bus system of the machine, that is what brain of the your weaving machine, that is called advanced technology, that is AT technology, control area network. If this get fails, your machine of 30 or 40 lakhs will not work. So all these cards are present in the control box, and it is having a cooling fan. If the fan get damaged, or if one of the card or 2-3 card get damaged, you have to directly purchase it from machine manufacturer, because repairing facilities are not properly available at the site. So see the CAN bus system. So this is what the advanced technology, how the electronics works. So next we'll see warp let off motion. So how the electronic warp let off motion is working. Very interesting thing is there. So suppose this is what let off module or electronic card of let off. For any electronic card of let off, we require 4 inputs, 1 2 3 4. So what are the inputs required for electronic let off cards here to work your let off properly? So here we require filling density input, that is what PPI. What PPI is required? What is the speed of the machine? What is the warp tension? What is the view? So this is what input to the warp let off model. So filling density means my 60 picks per inch is there, speed is 300 rpm, warp tension 5000 kilonewton, view is plane. So these inputs I am giving in the control panel. And from the control panel, the signal goes to the card, microprocessor card. And from the microprocessor card, the signal goes to the machine, and machine will be working accordingly. So what accordingly means, what the output we will get here, the let off of warp length will be there. So your beam will be getting rotating. After getting all these four inputs, accordingly it will release the warp accordingly. So warp release will be there. So let off warp length will be there. So according to your pix per inch speed of the machine, your warp will be released from the let off, and your let off beam rotates and releases some amount of warp. So this is what output. Second, whatever the let off of the length is there, that is what constant, and reproducible warp tension is there. So let off is constant, means what, 1 meter per minute let off is there. For every minute it will let off 1 minute only. So constant let off is there, even though diameter of beam get reduced from full beam to empty beam. The diameter is the let off is 1 meter per minute. So this let off is kept constant. Other thing here kept constant is reproducible warp tension. So we have seen here 5000 kilonewton is given here on the back raise, the warp tension, that tension remains constant. So here two things are maintained constant, one is the let off and one is the tension. Who is making this? Motor. So motor is working, let off motor is working accordingly the signal given to the machine input, the output will get. Again, third things here, what will get, fast response and producible when preventing start marks, and this response is also fast. So fast response, and the same results when we get start and stop mark is there, means what, when machine is starting and stopping, the start stop mark will not come. So this is what, how the let off heart is working. Input, 4 inputs are there, will get 3 outputs or 3 results from let off motor. If the electronic card is not there, let off card, all this function will not be working. So this is what let off. So note down the points in the slide. So this is what let off. So how the let off is working, see here. Here we are having a let off module or let off electronic card is there. For let off we are giving 4 inputs, that is filling density, speed, warp tension, view. Suppose filling density is 60 pix per inch. So 60 pix per inch input we are giving, speed is 300 rpm. Warp tension is 5000 kilonewton and view is plane view. So these 4 inputs we are giving in the control panel of the machine. These 4 inputs signal goes to the let off card is there, let off card, and this let off card the signal input gets, and let off card gives output, and this output signal goes to the motor of the let off, and this motor gives 3 outputs here. Okay, so 3 outputs is means what, let off warp length. So warp will be released from the beam after getting these 4 inputs. The warp will be released. Next, whatever the warp is released, it is constant, means what, if 1 meter per minute I am releasing from the beam throughout the exhaust, from start to exhaust of the beam, this let off length remains the same, that is 1 meter per minute, 1 meter per minute. So this is what one output from the let off motor. Second, we are getting reproducible warp tension. So 5000 kilonewton tension is at the back race. Same tension will remain when beam is full and when beam is getting exhausted. So two things we are getting here, the let-off length constant, whatever the warp release with the same constant rate it will be there. Again warp tension is constant, and next third will get fast response and producible when preventing start marks. So all these response are fast. This is what electronic card, and according to the electronic card input, the electronic motor works, let-off motor works, and we are getting this what three outputs. So when start stop of the machine is there, the starting marks may come. So that time also the let-off is working very properly, so that start and stop marks will not come. So this is the thing, four inputs and three outputs from the motor, and this is what let-off microprocessor card. So note down what is the input and output for the let-off or electronic let-off. So this is a warp cycle at warp let-off motion. So see here how the let-off cycle works, electronic let-off, that actual working here it has been given, and every shuttleless machine is having same let-off process or let-off working is there. So see the figure, we'll understand how it is there. So these are the four things we are giving: filling density, machine speed, view, and warp beam diameter. So diameter, full beam diameter we are inserting in the control panel. In the control panel we are giving this, the calculation at the controlling unit in the card, microprocessor card, this calculation takes place and it gives the output. It gives the output here. So these four things we enter and we get one result, how much the warp has to release. After calculation we'll get how much warp has to release. At the same time we'll enter actual warp tension value. So sensor is present at the let-off at the warp which sense the tension value. This input also comes to the machine, and also we are given targeted value tension. Suppose targeted value tension is 5000 kilonewton and actual also coming 5000. So from this again this is what another input. So input is there. So this is what input, targeted value tension. From that output will be one output, how much tension we have to keep, that will be the output. Two outputs are there from here, and it joins, and the signal is given to the motor, and motor accordingly release that much amount of warp. After getting this 4 and this 1, 5 inputs, we are getting what? One output, the speed of the motor, and accordingly the warp is released more or less. Okay, so again the diameter of the beam get reduced. That new beam diameter again it has gone to the what? Input. As the beam diameter get exhaust, the new diameter get added to the input. Again the calculation will take place. This will be what? Here output. Again from the tension value difference, actual and targeted, it gives the signal, and how much the warp has to release, it has been decided. So this is what cycle. For every release of the warp, new diameter will be measured, and again it has been sent to the what? Input. So like this the calculation start, and this calculation is what? Fast, and whenever any loom stoppage is there, original input values are stored, and whenever we restart the machine, that values comes again. So like this, storage of these values will be there. The frequent repetition of this reliability of this all these values are there whenever the normal machine working of the machine may be there, or you're taking forward and reverse slow motion, or braking and starting process, or speed change process is there, and or you're changing warp tension or filling wave tension, the value remains the same. So this is what warp cycle, how the let off works. To draw the diagram, so here we can see warp let off motion. To see here, so this is what electronic warp let off motor. Okay, and here is what sensors are present. So here the sensor to sense the warp tension at the backrest. Here two sensors are there. Again here one load sensor is also there. So 5000 kilonewton load means what? Here the 5000 kilonewton load is coming, and that is seen in the control panel. Okay, and again viewing will be there. At the fabric, at the front rest we are having the sensor to check the tension in the fabric, and here is your electronic cloth take-up ECT and EWL. So there is a synchronization between EWL and ECT whenever the machine is running, accelerating, braking, or in slow motion. Perfect synchronization is there. So this load sensor gives the tension value. So this is what actual tension value, and we have seen in the last figure targeted tension value. So this actual tension value we get by the sensor, and target is what? 5000 kilonewton. So there is any difference, your warp will be loose or tight, and accordingly the motor maintains the same tension. Okay, so this whatever the tension value is there, the signal goes to the let off card, and let off card accordingly adjusts the speed of the motor and keeps the same tension towards the 5000 kilonewton. If the 3000 kilonewton means what? The warp is loose, means the release of the warp will be less, so tension it will maintain. So this sensor plays a very important role in warp let off motion. So warp let off motion, it is not coming alone with the electronic card, it is having in combination with the sensor, backrest sensor and front rest sensor, fabric sensor. Now on our Dornier machine we are having only what? This sensor, fabric sensor. We are not having this backrest sensor. On fabric sensor we are trying to achieve the objectives of let off, that is what? Constant release of warp, constant tension and reproducibility. Three things we are getting the things here. Next here, warp tension adjustment. So in the figure we can see here two sectional warp beams are there, two different warp beams are there. See here, double width like our soldier. For each we are having what? Let-off motor. Here is the electronic let-off motor. Here is the, so two cards, extra cards will be there in the machine. Alternative sensors here we can see here. So either we can have backrest sensor or either we can have fabric sensor. Here both the things are here. Okay, this is what alternative sensor we are working with now. This may be there or may not be there. We are working now with the fabric sensors here. So it has shown red color, means what? Fabric sensor measures the tension in the warp and gives signal to the what? Let off, how much to release the warp. The signal is going like this. So double width, double sensors are there. So this is what tension adjustment. Continuously there will be what? Bidirectional signal will be there. Tension value will be going to the motor. Motor releases warp, again new tension will come, and again the tension signal goes. If 5 kN tension is there, constant release will be there. If 5 kN is not there, you have to adjust the speed of motor, automatically adjust speed, more release or less release, and maintains the 5 kN tension same. So see the figure. Next feature in the machine is start and stop mark prevention. So this is what very big hurdle in the heavy machines like shuttleless. Whenever the machine is running and when we suddenly stop due to the wet breakage or warp breakage, and again when we start the machine, there is a gap between last inserted peak and previous peak. So this gap means what? Start and start mark. Start and start mark. If the start and start mark is there, your fabric will be rejected in the export market and the value lost to the fabric will be there, and you have to cut the fabric there. So this can be prevented if you are having this feature, start stop mark prevention. Means what is happening here? This is what let off motor and this is what take up motor, and this is our reed. So these are heel frames, and in the front we are having the reed. So whenever your machine, any warp breakage or wet breakage is sent and machine is going to be stopped, your heel frame gets leveled. First the heel frame comes in the level condition, heel frames will be level, and reed goes at the back center and then rest. So due to this feature, the start and stop mark prevention is not there. Means what is happening here? When any signal we are getting for the stopping, before stopping, initiating, your heel frame gets leveled. So these are what all the heel frames get level in one line. Heel frame leveling will be there and reed goes back center and then machine stops. And again we can start the machine. So start stop mark is prevented. So what is the stories here? Whenever in normal case, if you are not having this feature, your machine stops in open condition. Warps in open condition means what? Open shade will be there. If open shade will be there, the tension on top warp line and bottom warp line will be there, and extension of warp will be there. Somewhat some amount of length will be increased, warp length increase, and again when we start the machine, this extra length of the fabric will be going, extra length of warp will be going in the fabric, and it shows a start stop mark gap in the fabric. So here only one thing we are doing here, we are stopping the machine in heeled leveling condition. So this is what one feature. That's why the extension or creep in the warp will not come. Next feature is like that. Here the reed goes to the back center and stops here. Means what will happen? When we are moving slow speed motor for taking one peak or two peak forward, if any peak we have to remove, short peak we have to remove, you have to rotate the machine 2 peak or 3 peak forward or backward. This forward and backward movement is done by the slow speed motor or peak finding motor, not from the main motor. So slow speed motor, it takes the machine one peak forward or two peak forward. This is what slow speed motor. At that time the reed has to be locked at the back center. If the reed is moving forward and backward, so what will happen? The edges of the warp get in the tension, creep will be there, added creep will be there, and again this problem of start stop mark will be coming here. So two things are happening here. One thing is heel frame leveling will be there before stopping, and also the reed get locked. So simple for peak finding also, this start stop mark prevention will be there. Means if any peak finding activity is there, your reed is locked at the back side, and on the edges of the warp from here and from right hand side and left hand side, extra tension will not be coming in the warp, and start stop mark will not be coming. So this is what the added advantage. If this feature is not there, your fabrics will be rejected. Mostly all the machines are coming nowadays with this start and stop mark prevention. So in the figure we can see another most important difference between other shutterless loom and Dornier rigid rapier. So we can see here, this is what 0 to 360 degree cycle is there, one timing cycle of the main shaft. So this shows what two curves like this, one up, one down, one up and one down. This is what velocity curve, and this curve shows tension of the weft. The wave peak shows tension. So this graph is of tension in the weft and speed of the weft. So two things we have shown in the graph. So A tension is for other machines, other Devas type of machine, tip to tip transfer. So see here, A means this graph will be there. This is what velocity, and this peak is showing, peak curves are showing what? Weft tension. So see here the tension A at the, so 0 to 60 degree, while gripping the weft on the left hand side, the tension is higher, you can see here. If this tension is very high, the weft breakage during the insertion will be there and machine will stop. And this B shows here for the Dorniers here. So this tension peak for the Dornier, and this is what weft velocity for the Dornier. Okay. So one thing we get difference, Dornier is having what? Weft velocity of weft is very high. The speed of the Rapier is very high. But here at the time of picking of the warp weft, the weft tension is very low than the other shutterless loom. A is here other shutterless loom peak, and B is here Dornier. So this is what tension peak, B is less than A. That is what Dornier, and that is what the Dornier machine is very successful to run it with what? High velocity. So two mountain shows velocity curve, weft velocity, and this peak curve shows weft tension. So A is for other shutterless looms, B is for Dorniers. So this is what the one best feature why the peoples are preferring, or industries are preferring Dornier shutterless loom. That is what one thing is there here. Again in the other figures here, the comparison of weft tension here. So this is what 0 to 360 degree, and this is what the tension 0, 50% tension, 100% tension here. And this green color is what? The tension, weft tension from 0 to 360 degree. Okay. And see here red color and blue color other weaving machines available in the market. So see here the tension peak of other is very high, above 50% weft tension. And see here the tension level of this Dornier weaving machine weft tension is very less than the 50%. Okay. And all these are above what? Above 50%. So this is what the stress in warp, or sorry, stress in yarn, stress in weft in the other shutterless loom is very high than the what? Our Dornier weaving machine. That's why Dornier machine is preferred for the high speed Rapier weaving machine for industrial fabrics. So see the graph. Also draw this figure and get understood. If any doubt is there, you can chat with me.